So in today's lecture, we're going to talk about or get introduced to radical chemistry, which is chapter 5. So reactions involving radical intermediates. We're certainly not going to be able to do justice to all of radical chemistry, and this is becoming much more prevalent in today's literature, but hopefully this is enough of a warm-up so that we can understand other types of radical reactions. Okay, so to start, we're going to kind of approach this the same way we looked at our other electron deficient center, which was the carbocation, by first approaching, what am I doing? Skipping down. By first approaching the stability of radicals. So free radicals lie somewhere between a carbanion, if they're carbon-centered radicals, I should say, lie somewhere between our carbanion in having a pyramidal geometry and a carbocation, which has a planar geometry. And we can draw the planar geometry with this unhybridized p orbital. Now somewhere in between these two geometries, there exists the radical. Now I like to consider two forms of the radical, at least as I'm thinking about this. I like to consider one form where the radical is sort of up, and that's rapidly interconverting between one where the radical is in an orbital pointing downwards. The truth is probably somewhere in between these two, but it's important to make note of the fact that whereas anions, these pyramidal anions, in many cases, we can find ways to kind of lock their geometry, particularly if we have the right counterion around, typically a metal of some sort. But I like to think of this as a shallow, the radical intermediate as a shallow pyramidal geometry that inverts easily, whereas it sort of depends on the situation if we're going to see a pyramidal geometry invert. Nitrogen pyramidals, which are neutral, invert readily. That's why we don't have to worry about nitrogen being forming a stereocenter, whereas other types of atoms or counterions being present, particularly with anionic geometries, we would see the pyramidal geometry maybe more slowly invert, and we could actually lock into a single configuration and get access to some stereochemistry. Okay, so this is just a picture of what radicals will sort of look like. What I want to get into now is radical stability. And it's not so much about what element you're attached to, though we could get into elements. Typically, it's nitrogen, then oxygen, and then carbon. So we see radicals are more stable on what seemingly is due to some electronegativity difference, and that may be the case. But where I tend to start to think about stability is substituents. Okay, if we have more substituents, and I'm going to capture that thought. I'm going to say not necessarily due to electronegativity, where carbon's the least electronegative and that sort of thing. Rather, there are substituent effects. Substituent, where more substituted is more stable. And that's the case here, just like it was with cations, because the radicals are electron deficient centers. So more substituted, more stable, because radicals are pretty closer to carbocations than they are to their neutral carbon counterparts. Okay, they're electron deficient. So this is just like carbocations. Now what that means is that when I say that oxygen is not as good as nitrogen, which is not as good as carbon, it's really taking into account the fact that we've got more substituents or valencies or more opportunities to add things to our carbon center. And that's because of increased hyperconjugation. And hyperconjugation, if you recall, this is just this term that suggests that electron deficient atoms or centers or areas are stabilized by nearby bonding orbitals. Oh, nearby is one word. Nearby bonding orbitals. Okay, there's another trend that we can look at just outside of things with substituents. We could look at monatomic radicals or single atom radicals. Monoatomic free radical stability. And what we see again is perhaps what looks like another electronegativity trend. And what I would rather think about is the stability of the charge, where fluorine radical is much less stable than the chlorine radical, which is less stable than the bromine radical, which is less stable than the iodide radical. So this is all for group 7. And if you recall, sometimes hydrogen is considered to be a group 7 element, depending on how you want to think about it. And if so, in terms of its radical stability, the hydrogen radical is way down there in terms of stability. Now, I would once again caution us to worry about electronegativity here and rather think about the atomic charge. The trend is probably due to the effect of polarization. So I'm going to write increased polarization. Now, polarization is something you don't have to often overthink. There are ways to kind of quantify this, but here's how I think about it. Bigger atoms allow charge to separate more easily or spread out more easily. Now, what do I mean by bigger atoms? Well, as you're going from fluorine, chlorine, bromine, and iodine, you're moving down in the periodic table, you're getting to bigger and bigger elements. And that's not because we're getting, well, it's not directly because our nucleus of our atom is getting bigger. Remember, the nucleus is quite small. It's because we're entering more shells to hold our valence electrons. And if we have higher numbers of shells, we're going to be further distanced from the nucleus and overall much larger. So you're just kind of moving out. So you've got your 1s orbital, 2s, 3s, 4s, 5s, 6s, whatever. You move further away, you get to a bigger orbital, which is just more space for the electrons to occupy. And if you have more electrons, more space for the electrons to occupy, you don't have to worry about things like too much electron density within a single area because it can spread out further. Now that helps to stabilize radicals as well, as radicals are sort of trying to figure out their situation. They're odd electrons, but the orbital is able to kind of handle that a bit better than if it were closer to the nucleus. Okay. So that trend can be separated or considered for other groups in the periodic table, other columns. So if you want to go to group 4, yes, carbon can make some quite stable radicals if it has substituents, but the silicon and tin radicals are even more stable yet. Okay, so that is radical stability. You know, some things I could just mention are unstable radicals that are unstable radicals that are difficult to access as we're proposing mechanisms. So when we're looking to propose mechanisms, some radicals that are difficult to access and therefore unlikely, well, not completely unlikely to be formed, would be things like the H dot radical, OR radical, although there are some alkoxy radicals that can be formed. The OH radical, and I should add that the OMe radical, I think, is an important radical in kind of celestial chemistry or outer space chemistry, if you will. And then CH3, the methyl radical, you can get access to it, but it's typically stabilized by something else. Things like methyl cations are entirely inaccessible. Like, you don't want to invoke a methyl cation in a reaction. It's controversial, but it's probably inaccessible. And if the methyl cation is inaccessible, then it's likely that the other electron deficient methyl center, the methyl radical, which is not up to an octet carbon, is probably very high energy and difficult to access unless you're introducing it by some other means. Though it's not impossible, like the methyl cation, I would say let's just not propose the involvement of methyl cations in our mechanisms. Okay, so that'll do it for radical. Well, no. I have another important point related to radical stability. Let's just say that if we can be stabilized by a bunch of groups, we should spend some time talking about whether or not, and I'm sorry, we had a hitch in the notes here. I can see it now. We can actually stabilize radicals by other ways. So this will be a little bit longer lecture. I should have just ended. Now everybody's excited. But I want to get into captivative effects. Captivative effects, talking about radical stability. What this suggests is that if you have a combination of an electron withdrawing and electron donating group, combination of an electron withdrawing, and that is, you need both. So you have both of these groups will provide enhanced stability for the radical. Okay. Let me just say this in shorter words. If you have an electron donating group and a withdrawing group next to a radical, you will have a greater stability than the stability of either an electron withdrawing or an electron donating group by themselves. Now let's take a step back and talk about stabilizing radicals with electron donating groups and electron withdrawing groups. So if I have an electron donating group, and let's pick on an oxygen, an OR, and I'm going to attach that to my radical, plus free radical. What does that look like? Well, it looks like RO, and now I'm going to put my radical on a carbon atom with two other R groups. Okay. Now, what we see here is that the electrons here can actually provide stability. The lone pair electrons, let's get a highlighter here. The lone pair electrons will stabilize the radical at carbon. Okay. Let's consider a resonance structure of that. Now, the way that we could go about considering a resonance structure is to try to make a bond with the oxygen atom using some of the lone pair electron oxygen atoms. All right, so I'm going to use a fish hook arrow to show the movement of one electron. And I'm going to use another fish from the carbon atom to make a second bond between carbon and oxygen. And I'm going to steal a lone pair. The result of the curly arrows is accurate, but we introduce a problem. That is, if you look at the carbon atom now has an octet, and we've introduced a resonance structure and delocalized the free radical over to the next atom. However, we have to cross this out. I'll cross this out in red because the oxygen has 10 electrons. If it's sharing 2 electrons with carbon by way of a pi bond, 2 with carbon via a sigma bond, and then 2 from the R group, that's 6 electrons from the bonds, 3 electrons from the oxygen atom, and we've broken the octet rule on the oxygen atom. And so even if I could put a formal positive charge, right, 6, I mean, is it positive? No, it's neutral. So it's formally neutral, right? 6 minus 3 minus 3 is neutral, but it doesn't matter. We've got not 10 electrons, excuse me, 9 electrons, but we've broken the octet rule. So what we have to do is we have to consider alternative resonance structures. And the alternative resonance structures that we consider will help us account for why the oxygen will stabilize a C radical. Okay, now this is going to look a little uncomfortable because curly arrows are really helpful for showing the movement of electrons when we're considering resonance structures. But resonance structures are just alternative depictions of the exact same molecule to show how electrons can move or how electrons can be distributed in different ways. Now, what we have to recognize here is that an alternative resonance structure is one in which the carbon atom has a lone pair of electrons and the oxygen atom picks up the free radical. Now, if we do that, the oxygen atom is now +1 and the carbon atom is now -1. So I could put a plus here and a minus here. Okay. To get between these two structures, we can't use any curly arrows. Rather, we just need to be aware that the oxygen atom is providing those electrons by way of resonance, but not through something that we can just show a curly arrow. I mean, what's happening here, if you're not following, is that we have this green, I'm going to highlight this electron in green. That electron is jumping over to the carbon in this alternative resonance depiction. So attaching that oxygen atom allows us to see, or attaching this oxygen atom allows us to delocalize some electron density from the lone pair into the carbon atom next to the into the carbon atom of the free radical. Okay, so electron donating groups sometimes are difficult to show by resonance how they're providing electron density. But if we've got a double bond, maybe it gets easier. So let's say we've got this radical. I'm going to put an R group here. What happens if I put this radical next to a double bond, which is part of an alkene? Well, then maybe it makes sense because this double bond is in conjugation with the lone pairs, and we could consider a resonance structure where we put the lone pair next to the free radical. But then once again, we have carbon atoms with lone pairs and free radicals. And so what I need to do is just consider, there's a negative charge over here. If I'm going to show this, this resonance structure stabilizing, free radical, which it does provide stability. I just need to hop that one of those lone pair electrons over to give rise to a free radical here, negative charge here, positive charge here. So I can show arrows to help me understand why the lone pair electrons can delocalize into the alpha position here. But then to get from a free radical, showing how that negative charge can delocalize and stabilize the free radical, I need to have the electrons hop over again. Okay. So it can introduce some challenges, but what I've, in terms of depicting how the electrons are moving around. But what I wanted to show you is that we can consider electron donating groups as viable options for stabilizing free radicals. And on the surface, that should make sense, because what we're doing is we are donating electron density into an electron deficient center. Okay. What we can also consider is stabilizing radicals with electron withdrawing groups. So stabilizing free radicals with electron withdrawing groups. Okay. So if we have electron withdrawing groups, we can actually soak up the electrons using a traditional resonance structure. So traditional resonance structures work, but we need to use fishhook arrows. This is kind of cool because it allows us to stabilize. Overall, this is going to allow us to stabilize free radicals, which are electron deficient centers, using electron withdrawing groups. Usually we can't stabilize electron deficient centers like cations with electron withdrawing groups because we're stealing more electrons that they don't already have. But if you put a carbonyl adjacent to a free radical, for example, you put a carbonyl adjacent to a free radical, we could pop the electrons up and onto the oxygen in the traditional kind of carbonyl resonance structure. And then we can actually, shoot, I went the wrong way. Let me just back up. We can go here to here and then up to here. Sorry about that. I was thinking about something else. Okay, so we're going to use 3 fishhook arrows, one to form a pi bond, and then we're going to pop one of the remaining free radical up and onto the oxygen atom, and that will provide some stability, although not a great deal of it, because the oxygen atom is now, well, it's neutral still, but now it is soaking up the radical. So maybe there's a better way to show the movement. Maybe there's a better system to stabilize our free radical. So this is still a better structure. But if you recall from organic 2, more resonance structures equals a more stable free radical. More resonance structures equals additional resonance structures equals a more stable free radical. Okay, but alternatively, maybe it would be more helpful to consider a pi system like benzene. What if we put a free radical next to a benzene ring? This would be a benzyl radical. We could provide some stability now through the pi system and draw a bunch of resonance structures. Now, obviously, we break aromaticity, but we still provide some stability for our free radical intermediate by just pushing the free electron around the ring system. Okay, so there are some examples where we can have pi systems that actually withdraw electron density by way of, I guess they're kind of donating. So still, I guess it is kind of donating the electron density. Let's just get back to the captivative effect. So in the captivative effect, what we see is that captivative effect is both electron donating groups and electron withdrawing groups stabilize free radicals. Stabilize free radicals. And they do so more so than the sum of the electron donating group and withdrawing group by themselves. Okay, so let me say it this way. An electron donating group is going to stabilize the radical somewhat. The electron withdrawing group is going to stabilize. They both stabilize the free radical. But when you put them together, okay, putting them together leads to more stability than just the sum of the two by themselves. Okay, now a great example of this is if we have a dinitrile free radical. So if we put a dinitrile free radical, this radical is stabilized by the 2-nitrile, and nitrile would be a CN group, nitrile electron withdrawing groups. Okay. But if we introduce an additional substituent, now I realize I'm adding a substituent, but what you get is if you introduce an electron donating group in addition to these two electron withdrawing groups, I'm going to put a nitrogen here with its lone pair of electrons next to that free radical. We are going to get enhanced stability, much more stable, because we have both electron withdrawing and donating groups. Are present. Okay. All right. So I just wanted to mention that in the context of the captivative effect. Now what I want to move into are some other stable radicals just briefly. So what you can do is you can actually make nitroxyl radicals. Nitroxyl radicals are when you take some sort of nitrogen species and you oxidize it. If you oxidize the nitrogen species, you get to this species. This is a hydroxylamine. Okay, so we oxidize this. Now, we oxidize the nitrogen by introducing an oxygen atom. And what you can further do is you can do a single electron removal of that hydroxylamine to make a nitroxyl radical. Okay, so let's look at that. I'm going to draw the lone pair electrons on the nitrogen atom explicitly. I'm going to do a -1 electron oxidation. And I'm going to remove one of the lone pair electrons to make this intermediate structure. Now, it turns out you can do this one electron removal under numerous conditions. You can even use electrolysis or an enzyme-mediated pathway to remove that that free electron. Now, if I do that, I now have a nitrogen radical, and the nitrogen now is positively charged because group 5 element minus 4 bonds minus 1 lone unshared electron. Now, while we can show a resonance contribution where the electron density on the oxygen lone pairs can stabilize the nitrogen, actually, what is even easier to do is a chemical reaction with a fairly weak base to deprotonate the oxygen atom, because then instead of having a mere alcohol, now we have stability from the strongly electron donating alkoxide. We have a full-blown alkoxide anion next to this nitrogen. Now, I don't want to push the negative down with the positive to make a double bond, because that will break the octet rule. Now, this is actually a stable or persistent radical. Nitroxyl radical is stable. And if it's stable and long-lived, that is, you can put it in a bottle and keep it there for a long time. We have some in the chemistry stockroom at the college. It's stable and long-lived. We would call that persistent. That is, it will persist. It will not find a way to kind of collapse on itself, react with oxygen, or do something else. It is stable. Now, it all comes from these methyl groups. This is actually, well, the methyl groups aid a lot of this. The methyl groups and the oxygen anion are what make this possible. This is called a tetramethyl. You can see tetramethyl. There's 4 methyl groups. Piperidinium. Well, piperidine is a 6-membered ring with a nitrogen in it. So just picture a 6-membered ring with no double bonds and an NH. That's piperidine or piperidine. Piperidinium because it's positively charged, and oxide because there's an oxygen attached to it that does not have a hydroxyl group on it. Well, if you do TEMPO, you get to the tempo radical. Now, tempo is a really cool radical because it can do some interesting chemistry. Namely, if you take a hydroxyl group and you react it with tempo, you will form an aldehyde with no over-oxidation. Plus, the oxygen has been, the oxygen of the alcohol has been oxidized, and the byproduct of the reaction, I'm pretty sure, is just the hydroxylamine. And so we would have to, and so anyway, this is a byproduct that's easy enough to deal with. And the starting material is easy enough to come by. So you can usually just have copper, and I think it's copper and tempo that are used to kind of make you can actually generate a catalytic system. You can use enzymes, you can use electrolysis. Anyway, a really green procedure that gives rise to a way to generate carbonyls from alcohols without any substantial byproducts. Okay, that's a lot of talking. Let's at least take a break. I'm a little winded. There's a lot of noise downstairs in my house. Okay, everybody, we'll see you next time.